Okay, so we're talking about determinants and elementary operations. If product, well, if E1, E2, E2, E3, E2, E1A equals the identity, in other words, if these are the elementary matrices used to reduce A to the identity, then E1 inverse, E2 inverse, E3 inverse multiplied by both sides of this matrix gives you this equation. Well, on this side, E1 inverse, E2 inverse, E3 inverse times the identity doesn't change anything you multiply it by, gives you this. On this side, well, we saw it before, so I'm doing this rather quickly. E2 inverse, E3 inverse times E3 is the identity. And then that identity, say, times E2 is just E2. So now you've eliminated E3 inverse and the E3. And then you're going to have just E2 inverse times E2. And that's going to give the identity. Multiply that identity by E1 or by E1 inverse, whichever. You're going to get just E1 inverse times E1 times A. And E1 inverse times E1 is the identity. And the identity times A is A. Now we looked at this in more detail previously, just refreshing our memories. So the determinant of A, of course, equals then the determinant of E inverse, E1 inverse, E2 inverse, E3 inverse. We can write, of course, using the kind of absolute value notation for the determinant of A is then the product of the determinants, because the determinant of a product of matrices is the product of the determinants. We haven't actually proved that, but we're going to prove something here. So if E, okay, there's some rules now. The determinants of these matrices are really easy to figure out. If E has the effect of switching rows, then the determinant of E is -1. We're going to actually prove that in general for matrices. Switch rows, determinant is going to change sign. And since the determinant of E is 1, that means if you change a sign, it's going to end up being -1. If E multiplies a row by C, then the magnitude of E is C. Now we're talking about if E has the effect of multiplying a row of the A matrix by C, its determinant is C. If E adds a multiple of one row to another, its determinant is 1. And that's really convenient because you do a lot of adding multiples of rows to others when you're reducing typical matrix and you don't have anything to keep track of. So really all you have to keep track of is the determinants when you switch rows, which is -1, and when you multiply a row by a constant. So really you don't even have to keep track of the determinants of the elementary matrices themselves. You know now that this is going to be the case. Okay, well, at least you know now if you believe the proof that follows. So why does switching rows change the sign? Well, very simple inductive argument, but you might not have seen many inductive arguments. So this could be an introduction to inductive arguments, which are very important in mathematics and in the mathematics that you're likely to encounter in your curriculum. Well, okay, comes down to this. We easily prove that the determinant of a 2x2 matrix changes sign if you switch the rows. Because, well, here's a matrix, A11, A12, A21, A22. Switch the rows, you get A21, A22, A11, A12. The determinant of this first matrix is A11, A22 minus A12, A21. Determinant of the second matrix, well, you got A21 times A12, but I'm going to write that as A12, A21. So it matches up with this, and notice it has the opposite sign here. And then A22, A11, I'm going to write as A11, A22. It has the opposite sign here. So these are equal and opposite. So that establishes it for a 2x2 matrix. Now for a 3x3 matrix, then it follows that, well, here's a 3x3 matrix. And here's the same matrix where I switched the second and third rows. I expand on the first row, on the row I didn't switch. So if I switched the first and third rows, the second row would be unchanged, so I'd expand on the second row. So the expansion, as we know, is this times the minor you get here, here it is, and this times the minor you get when you take out this column and this row, here it is, and then this times the minor you get right here when you take out the row and column of A13. So I wrote this one down and I wrote this one down, and I didn't have room to write this one down because I'm afraid of the watermark, okay? The banner that WebAssign or that Zoom puts across there. So I'm going to lower the screen a little bit, come on, to avoid that watermark. Okay, I think that avoids it. I think it goes down here. Well, if I write down the expansion, you notice that the minors are all on the second and third row. So that when I've reversed the second and third row, this first minor, A11 times this block here, is going to switch the second and third row from what we had here. Same thing will happen on this minor because, again, it involves the second and third row. And then the third one that I didn't write out, same thing. And since we've just proven very easily that this works for a 2x2 matrix, it works for all these 2x2 matrices that we get when we expand this thing. And that changes the sign of every one of these 2x2 matrices, which changes the sign of the entire determinant. If I had switched the second and third rows, I would have done the expansion on this row. And the same thing would occur, and I'll leave it to you to sort out, but it's pretty straightforward. Okay? So that outlines how we prove it for a 3x3 matrix, and then do the same thing for a 4x4. Okay? The 3x3 matrix inherited the property of changing the sign when you switch two rows from 2x2 matrices, because all the minors involve 2x2 matrices of the two rows that you switch. Changes all the signs of the minors, which changes the sign of the entire determinant. Same thing's going to happen here. Okay, here's two 4x4 matrices where I've switched the second and the fourth rows. Okay, maybe circle that the way we did before. And it occurs to me, it might be clearer if I circle the rows here and show that, yeah, well, I'm not going to circle over here. Okay, anyhow, there they are. And if I do the expansion, again, assuming that the first row isn't one of the ones that I switched, and if it is, then I'll expand on one of the ones that I didn't switch. Okay, I could as easily expand this on the third row, okay, but I expand it in the first row. Okay, expanding on the first row, we get the first minor is going to be this. This is the minor block you get here. And the first minor on this matrix is going to, again, be this. And you notice that those minors involve the second and fourth row inevitably, because we're expanding on a row that we didn't switch. And we established then that we have equal and opposite signs here and here. The same thing is going to happen on the minor that we get on the A12, the 1,2 cofactor. The minor is going to switch the same two rows and switch its sign. And same thing when we do the minor for the A13 and the minor for the A14. Okay. all those minors involve the second and fourth row. Second and fourth rows get switched, so the minors all change sign. Everything else stays the same. The determinant changes sign. And then we say, okay, well, that's great. So we could do the 5 by 5 since we know the 4 by 4s work. And then we can prove it for 6 by 6 since the 5 by 5s work. What if we want to do a matrix that's 1,000,000 by 1,000,000, 1,000,000 rows by 1,000,000 columns? Okay. We don't want to have to prove it for 6 and then prove it for 7 and then prove it for 8 and then prove it for 9 all the way up to 1,000,000. It would take hours, years, lifetimes. But we can say in general, if it's true for an n by n matrix, then switching rows of the n plus 1 by n plus 1 matrix would change the sign of the determinant. In other words, if it's true for n by n, it's got to be true for n plus 1 by n plus 1. Why is that? Because all the minors, I should say all the minors of the n plus 1 by n plus 1 matrix, to be sure we know which matrix we're talking about, are n by n, and they all change sign. Now, formal proof, you got to do a little more writing, a little more argument, and you got to state things a little more precisely. That's an important proof, and I kind of expect you to be able to do that. Okay, and you can read it in your book, see how they address it a little more formally than I did, but the ideas are all exactly the same and really pretty simple. But if you haven't seen an inductive argument, look up mathematical induction. Spend 15 minutes reading it. Start getting your head around it because it's important. Okay, well, there we have that. Okay, so we just proved this. We can prove this. And proving things is important because then you understand why they're true so you don't misapply them. And it also makes it easier to remember the properties. If you understand how they're proven, you can just kind of go through a proof in your head and you get in the habit of kind of checking yourself whether what you're doing makes any sense or not. You get in the habit of being a little skeptical and you just develop a much deeper understanding and a much better ability to solve problems, okay? To construct solutions, to do creative things, all that stuff. Well, okay. We want to show that multiplying a multiple of one row, adding a multiple of one row to another doesn't change the sign of the determinant. So it just comes down to why. And why does adding move one row to another not change the determinant? I can actually move the camera back a little bit to get the whole board. I didn't do that before because we were doing a lot of looking over here, and this part of the board gets a little small. Actually, I'm going to take a second. Okay. That gets significantly easier to read. I just clean it out. Tell me what you think. But I'm having trouble figuring out how to do a frame for that without getting in the way of my feet. Okay, so how does adding a multiple one row to another not change a determinant? Well, first. And this is true for any determinant, not just elementary matrices, but of course elementary matrices are matrices, so they have determinants and they inherit this property. Okay, or they possess this property, they don't have to inherit it. If a row of A is all zeros, then determinant of A equals 0. Now that should be a familiar property. It makes a matrix non-singular. You know, matrix is non-singular if, when you reduce it, it reduces down to a matrix with a row of zeros, and that, because it's a little bit circular, but because of what we're doing, that proves the property. But the easiest way to prove it just expand the matrix in that row of zeros. You know, 0 times 1 minor plus 0 times the next minor plus 0 times the next minor, or minus 0 plus 0 minus 0 plus 0. But it doesn't make any difference. They're all 0. Everything's going to be 0. So that's really easy. Okay. Now, excuse me for a second. Okay, so let's do an example. I'll just do it for 2 by 2. Okay. Now let's add C times the first row to the second. And I probably need a little more room to write this out. Once more, reminding myself to think ahead, not that it does any good. And I'm adding to the second row. Okay, I think that's written clearly enough you can read it. Okay, so expanding this, we have this times this, and it's not plus, it's minus. And that equals A1, 1, A2, 2 minus A1, 2, A2, 1. Plus C times A11, A12 minus A12, A11. Okay, A11, A12, A12, A11. And what's A12, A1, A1? Well, these are equal. So when you subtract, you get 0. So that's 0. Okay, well, in the same way that 3x3s inherited the property from 2x2s, and you can think this through, the way that 3x3s inherited the property that the determinant changes sign when you switch 2 rows. In that context, the 3x3s inherited the property from the 2x2s. Same thing's going to happen here. If you multiply, if you have a 3x3 and multiply everything in the third row by, or add C times either row, second or third row, C times a row to the third row, think C times the second row to the third row, then all the minors that you get when you expand on the first row are going to do the same thing. They're all going to have this sort of thing, okay? And if you write it out, you'll see how it works. So I don't want to take the time to write it out because we've got limited time at this point. Okay, so it's true for 2x2s. So true inherits, since the minors are all 2x2. And now n plus 1 by n plus 1 inherits from n by n. Since the minors are all n by n. Meaning that once we actually want to write this out for an arbitrary n by n matrix. And I don't recall if your book actually does that, but we write it out for n by n matrix. You're going to have A11 through ... A1n, A21, A22, ... A2n, and all the way down to AN1, AN2, ... ANN. Now, if you add C times the second row to the third, all the minors are still going to have the elements that you get from the sum of the second and third row with that C in them. And everything's going to, and then, okay, I'll just say all the minors are going to be n by n. And then the n plus 1 by n plus 1 is going to have the property. Okay. And how that proves that if a row is all zeros, the determinant is 0. Okay. Actually, that's not what it proves. It proves that adding a multiple of one row to another doesn't change the determinant. Now, I was going to use the fact that if a row of A is all zeros, then the determinant is 0. And that gets a little more involved, so I'm not going to, looking at the time, I've got 7 minutes. I'm not going to have time to do that. So it's maybe a little misleading, but it's still good to know that you can easily prove this row is all zeros. Then you just expand on that row and you prove that the determinant of the matrix is 0. Okay, so now we have this scheme of elementary matrices. We can do the determinants. And this shows since the determinant is this product, and I should say, I don't have some room to write it in here, provided the determinant's not 0, so the matrix is non-singular. So that A reduces to I, so you do this whole thing in the first place. We can find the determinant of A by reducing it to I. Keeping track of every time we multiply a row by constant. And every time we switch 2 rows. Now, I didn't quite write this out correctly, but I didn't have room. Every time we multiply a row by a constant, and we want to keep track of the constant. Okay, we want to keep track of the constant and the fact that we multiplied the row by the constant. And we don't really have to write out the elementary matrices. Now, I could have proven this without using elementary matrices. And matter of fact, in proving the properties of elementary matrices, I just proved it directly for any matrix. But it's worth seeing it within the scheme of the elementary matrices. The other thing is, since I'm multiplying by inverses, if one of these matrices multiplies a matrix by constant C, its inverse multiplies the determinant by the reciprocal of C. So you gotta watch that. In other words, if you got to multiply a row by -3 in order to do the row reduction, then the matrix that you end up with will have 3 times the determinant of the previous matrix. Okay, so if you want the determinant of the previous matrix, you're going to have to multiply that by 1/3. Okay, well, again, the assignment on elementary matrices and determinants, I don't think is due until a week from today. And WebAssign has probably decided to kick me out by now. But let me, not yet. Okay. Yeah. And what you have for the next time is just the assignment on the determinant of a matrix. And we've used the properties of determinants and the, well, I think we've got a pretty good review here of what we did a week ago on determinants, expanding by minors and so forth. So if you need to review what we did, it is there on the assignments page, and please feel free to do so. Matter of fact, I recommend that you do. Okay, well, that'll do it for today. Any questions? Okay, well, if you do have questions, email me. I'm going to have to close out here in just a minute or two. So I'll give you a couple of minutes, but then I have to get started for my next class. You're welcome, Donovan, Chris. Okay.